Okay, so this is our Ruyer reading group coming back after our couple weeks of hiatus. So we're continuing our reading of Cybernetics and the Origin of Information. Last time we had just begun chapter 5, but we just before we started recording, we decided we're gonna like pick up from the beginning of chapter 5 again, just because we're only a couple pages in, and it was a little while ago. So we'll go over the first couple pages again. But yeah, I think it was like 2 pages in that we had gone through. Yeah, so chapter 5, the origin of information. So has to do with a question that we saw in the Simondon reading, and also I think in the introduction to this book about like the question is sort of if information is understood in terms of transmission of information. So like this sort of communication theory, information theory account of information, which is like a sort of quantitative account of how can you transmit a signal without losing content or information in that sense. So if this is the understanding information you're working with, then you can only ever preserve or lose information. So a telephone line or a Wi-Fi connection, whatever it is, some sort of channel or medium for transmitting information can only ever, at best, preserve exactly the same amount of information as was at the outset. And then in practice, any channel is going to have some noise, even if it's very minimal and there's error correction and so on. So in practice, you're going to lose a certain amount of information. But then the question, of course, arises, where does that information come from at the start? Like if all the processes you're dealing with can at best preserve and in practice will always lose a certain amount of information, then how do you have information to transmit in the first place? And this was something that Simondon had objected against, or he'd taken this to show that like the sort of technical information theory account of information was a sort of limited theory. It describes a certain domain of problems, and it can be used to solve problems in communication engineering and so on, but it can't really account for the full set of things or phenomena that we use the word information to describe in sort of everyday language. And so he had come up with this, so Simondon, again, he had sort of presented this idea of a kind of tension of information was the term he used, which is maybe not that clear a concept, but he tried to, he sort of appealed to the way that some concepts or some phenomena, I guess, and to use a very general term, some phenomena have the power of structuring their environment. His sort of like standard image for this is the seed crystal dropped into a solution, which crystallizes the rest of the solution around it in a certain structure. And so he sort of compares this process to the way that a certain concept, for example, can sort of make everything fit together, where once you learn a certain concept, you can say, this whole domain that seemed confusing before now sort of makes sense, in the light of, applying this concept to it. So I think we can maybe sort of keep this idea in mind as we're reading this chapter from Ruyer, because he's sort of starting from the same problem of like, what does it mean to, what does information mean if, or where does information come from that is then later sometimes transmitted from from a receiver to from a transmitter to a receiver. We have to have some sort of information generating process or some origination of information that is not itself a kind of transmission of information, because he wants to sort of criticize or I guess delimit the scope of validity of the sort of cybernetic approach to these problems, which tries to understand everything in terms of information transmission, and try to, especially in the case of human beings, trying to understand human beings in terms of these information transmission processes like you would find in a machine. And so Ruyer is going to argue that if we sort of try to reduce the human being who sort of puts together a message to like a process of information transmission, then we end up in this sort of paradox of like the generation of information would be reducible to a process that can only ever preserve or degrade information. And so, yeah, we would have like a sort of well, it's analogous in some ways to thermodynamic problems relating to entropy, where a thermodynamic process can only ever lose order, or preserve in the best case, or in practice lose order. So you never have a thermodynamic process in which a whole system will sort of spontaneously take on order. And so here the key is that this is a closed system where you don't have any energy coming into the system or anything like that. But if you like take a so this is again, this is like a sort of a difficult point, because in thermodynamics you can show that you're dealing always with statistical processes or statistical concepts. So you can so I mean, some of the examples you get, like say like you have a piece of paper and you light it on fire, it will burn and turn to ash. So from a sort of statistical mechanics or like thermodynamic perspective, you can only say that, say, the clump of ash left on your counter is very unlikely to sort of spontaneously just become a piece of paper again. I think most of us would regard that as not just very unlikely, but actually impossible. But yeah, so here in this case, we see that the paper has a certain structure of fibers, and and ultimately these come from like cells of a tree or some other plant that have been processed in a certain way. But once you burn it, all that structure is sort of degraded into this powder. And so the order or structure that was there in these fibers of paper disappears in the process of burning. And so this is like an entropy increasing process, and thermodynamic processes in general increase entropy within a closed system. And information and entropy are sort of converse concepts, in the sense that the same equation that defines entropy, you just put a minus sign in front, and that defines information. And so like the process can only go in one direction, to increasing entropy or decreasing information. But then it leaves you with a big question mark of like, where is the sort of starting point of this process? Like, where does that first quantity of information come from, if the processes we're thinking about and using in our theory can only ever go towards a decrease of information? So that's sort of like the big picture of what's going on in this chapter. So yeah, let's get into the chapter. If someone would like to read.
I can read. Chapter 5, The Origin of Information. R.A. Fisher, Claude Shannon, and Norbert Wiener were the first to define the notion of the quantity of precision. As we have seen, basic information is the alternative, quote, yes hyphen no, or any other quote unquote binary decision, 1 or 0, right or left, and so forth. This is the unit of information, or quote unquote Hartley. And there is a figure 5.1 with a line segment AB, where the left direction is pointed towards 0, the right is pointed towards 1, and then there's a 4 vertical dotted and drawn through the line segment with lowercase a at the smallest segment. If we have to localize a point on a line or describe it with perfect precision, the quantity of information must be practically a description, a localization, or a measure are never perfect. Let's consider a point P, which we simply know is situated on some part of a line between A and B. We are then informed by 0 signifying the left half, or by 1 signifying the right half, that it is in the left half, then in the right half of this left half, and so on. The binary number in the form 0, 0, 1, 0, 1, 0, 1, which expresses our information, can never be an indefinite series of ones and zeros. Information has a limited precision. It only gives a zone of probability, lowercase a, b, between capital A and capital B. Here, for example, the 5th digit after the comma is undetermined. The quantity of information is limited to 4 digits after the quantity of information gained by the passage from capital AB to lowercase ab amounts to a logarithm of a probability. The formula that expresses it is exactly the formula for entropy, which is also a logarithm of a probability with the opposite sign. Information is negative entropy. This result was surprising and even seemed quote-unquote sensational. It is, however, only natural and is easy to understand. Suppose that the line capital AB represents a metal bar at a certain. We raise the temperature of zone lowercase ab. The second law of thermodynamics implies that the temperatures soon equalize themselves and become uniform. The entropy of the system increases. While in the previous example, the information about the location of point P between capital A and capital B increased as the zone lowercase ab was narrowed. In the case of the heated bar, on the contrary, the entropy increases as the temperatures equalize and the zone lowercase a merges with the whole capital A. The increase of entropy is then equivalent to a decrease of information, and vice versa. Once again, there is nothing extraordinary in this, since information is synonymous with structure or organization, and entropy is synonymous with disorganization. As long as the zone lowercase ab is at a higher temperature than the rest of the bar as a whole has a certain degree of structure. It is quote unquote informed in the etymological sense of the word, and therefore, as an observer, I am informed in the ordinary sense of that a particular event has occurred in a. When entropy has become maximal, the thermal agitation is homogeneous throughout the bar, and information is met. The zones of probability previously distinct are fused. If I write with bad chalk on a bad slate, the rapid homogenization of the chalk dust over the entire surface of the slate is a phenomenon analogous to an increase in and at the same time a loss of the written words become illegible. If the quote-unquote static on the telephone or radio reaches a certain intensity, or if the modulations are too weak and descend to a level of fluctuation that causes static, the speech becomes indistinct. That being said, since any machine, no matter how sophisticated, including calculating machines or feedback automata, can only increase entropy as they operate according to the principles of thermodynamics, it is evident that they can only decrease information. The background noise in the telephone or the radio can scramble the message, but it is impossible to imagine that the pure chance of the fluctuations can reconstitute a message that has been scrambled or create information out of nothing. It is as impossible or as improbable as a kettle freezing when put onto boil. Entropy goes in the direction of the most probable states. Information, which has the opposite sign, is therefore a quote-unquote anti-probability, or to use an old expression of Arthur Eddington's, a quote-unquote anti-chance. Chance cannot account for anti-chance. The mechanical communication of information by a machine cannot account for information itself, since the machine can only degrade it, or at best preserve it. Cybernetics cannot escape the contradiction. If, quote, no operation by a machine on a message can gain information, quote, and if, on the other hand, quote, there is no reason why the essential mode of functioning of the living organism should not be the same as that of the automaton, then where does information come? Yeah, so he doesn't seem to be saying a lot more than what you covered in the introduction to the session. As I understand it, the basic point here is that if information is the negative of entropy, then well, actually, I think that's a slightly point. I was going to say if information is the negative of entropy, then the creation of information will always be a global increase of entropy. But I don't know if would take issue with that point. His argument seems to be that the random fluctuations in, for instance, the background noise of a telephone line or any other random process is never going to result in an operation of information or a creation of structure or a decrease of entropy on its own. Yeah, I wonder what I was reading recently about this theory about kind of the earliest like precursors of life having basically a thermodynamic like dissipative origin, so that I'm not familiar with the details, but somehow the most efficient way to get rid of this excess solar energy was to take on a more complex form, or a more complex form being more efficient at sort of shedding the excess solar energy, which does kind of seem like a sort of spontaneous and not like non-intentional creation of information. But maybe he would distinguish, I think as he will later on, between different kinds of information, and would not see that as sort of the same kind as the kind of information that a human being is creating when they're talking
Yeah, that's an interesting example of this sort of dissipative system example, because there's been quite a lot of yeah. So maybe just to back up a little bit. Thermodynamics in the sort of classical 19th century sense had to do with closed systems. So this is a system that is not receiving or emitting any energy or matter. So you have like, and obviously this is a sort of idealization, because any system that really exists in the physical world is going to have some sort of exchange of matter or energy with its surroundings. Otherwise, it would be completely undetectable. But you can sort of approximate this condition, surrounding something with isolating, like a thermal isolation of some kind, etc. And in this closed system, of course, there is this, this constant increase of entropy that the system only loses order. It becomes more and more homogeneous over time. But in the case of dissipative systems is an open system, because, like in the case of life arising on the Earth, for example, you have this constant influx of energy from the sun. We can put a Georges Bataille glowing eyes emoji in the chat here or something. But yeah, so you have this constant influx of energy from the sun, which is sort of the impetus or the motor that allows for the formation of structure out of something that was not previously structured. So you have this sort of soup of chemicals or whatever it is that receives this input of energy. And then, as part of this process of sort of dissipating that energy, it forms some kind of structure. And you can see this even, like, one of the sort of classic examples of this is you just have like a pan with oil in it, and you put it on top of a stove, and then at a certain temperature, or even water, I think does this as well. At a certain temperature, as it heats up, instead of just having sort of random, like undirected movement of the oil or water particles, the liquid starts to form these sort of hexagonal cells, so that it's sort of circulating in this structured pattern. And similar types of things happen. Like a hurricane or a tornado, for example, involves like water and air interacting in certain ways, and when the temperature and other conditions are right, the sort of random or undirected movement of the air and water get transitions into this much more structured form, which then, like in the case of a hurricane, takes on like the existence of that structure, sort of accretes more structure around it. So that you have like a small, say, a tropical storm, for example. If it's circulating over warm water, it will absorb more and more water into it, which makes it bigger and bigger, which allows it to grow more, etc. But again, here this is not a closed system. You don't just have like a swirling, like a massive air swirling around inside a closed box, for example. It's this massive air swirling around in this sort of vortex over warm water, where that thermal energy allows it to sort of take on more and more structure. So this is so at the time Ruyer is writing, there's not really, or there's much less sort of awareness and understanding of open thermodynamic systems than of closed ones, and so he's sort of focusing on the closed systems. But I think, well, I mean, there's a sort of question of to what extent, or how do we sort of understand the difference between open and closed systems, and which one is more fundamental? Because in some sense, the universe as a whole is presumably a closed system that's not receiving. I mean, if we think of the universe as the whole sort of physical world, that there's no anything that is physically interacting with us and with anything that directly or indirectly with us is part of the same universe. Then it would be sort of by definition a closed system. It wouldn't be able to receive energy or matter from anything outside of it, because then whatever that was would also be part of the universe. So in that case, if the universe is a closed system, then it seems that you would have to have this sort of constant decrease of structure, or this constant increase of entropy in the universe as a whole. But of course, that doesn't mean that in certain local portions of the universe, like the Earth, you can't have an increase in order as a result of this sort of structure structuring operation coming from this inflow of energy from the sun in our case. So yeah, it's maybe a bit more subtle than the way that Ruyer presents it here, because so in an open thermodynamic system, you can have a sort of spontaneous formation of structure as a result of this influx of energy. But if you sort of zoom out and widen the scope and look at not just the one, like if you don't just look at the Earth, but you look at the whole solar system, for example, the whole solar system is losing order, or the entropy is increasing, in the sense that the sun, the sort of nuclear reaction that is powering the sun is sort of burning its way through the fuel that makes up the sun over the course of many millions of years. And so the capacity to perform work is constantly decreasing. At some point, there won't be enough of the hydrogen left in the sun to continue that nuclear reaction. So there's like these sort of complicated processes that happen with the sun expanding into a giant and then contracting again, I believe. So like the whole solar system as a system, at the early formation had much more structure. It had much more capacity to do work, sort of potential within it. And then over time, a lot of that capacity to do work is being sort of dissipated out as radiation flowing out of the sun, towards the planets, and out into empty space, etc. And then eventually it will just be completely dissipated and more or less dead. Our sort of local Earth point of view involves this increase in order or decrease of entropy. But then if you zoom out, that sort of local increase of order is sort of you can think of it almost as like an eddy in the process of this sort of flow of order down, or flow of energy down the sort of order gradient. So in the same way that like a stream flows downhill or flows towards sea level, but then you can still have an eddy if the stream runs into an obstacle, a rock or whatever. It might sort of flow backwards and form this sort of whirlpool at one point, but that whirlpool is formed sort of by means of the energy that comes from the downhill flow. And so the Earth, or all the different organisms and incredibly complicated structures that exist on the Earth are just the sort of whirlpool in the flow of energy down that gradient, in the whole solar system. Okay, so we can go on to the next bit. Sorry, where did we end? What's the ending point where we stopped?
We're at the top of 83.
Okay, great. Okay, so I'll read the next bit. A similar question was raised at the end of the 19th century, precisely when the principle of the degradation of energy was popularized. Where, it was wondered, do quote-unquote higher forms of energy come from? Immediately, metaphysical and theological answers were drawn, supposed to be valid for the entire universe. They even provided a new proof of the existence of God. Since the universe is like a clock whose spring is unwinding, someone must have wound up the clock in the beginning. The unfashionable, quote, clockmaker God, unquote, of the 18th century returned in the guise of the, quote, clock winder, unquote. God would no longer be the watchmaker of Voltaire and Paley, he would be the winder up. But problems that concern the universe as a whole easily arouse the suspicion of being poorly posed, and probably rightly so. There are very few philosophers today, and even fewer scientists, who are much concerned about the, quote, initial winding up, unquote, of energy. The problem of the origin and creation of information is, on the contrary, precise, limited, and pressing. If A speaks to B on the telephone, or A leaves B a message on a slate, the origin of information apparently has some relation with the organism A. The message sent is obviously not created ex nihilo. Its conscious sender has himself been informed, instructed, and educated in a social milieu where innumerable instruments of information exist. But in this particular case, he nonetheless plays the role of a source of invention or creation. The one who dictates a message invents more than the one who writes down the message. He is a, quote, winder up, unquote, of entropy, to the exact extent that he is an active informant. It is absurd to suppose that only pure transmitters exist in the world. Before communicated information, there is created information. One is almost tempted to stop the discussion here and to condemn cybernetics without further examination, as one condemns perpetual motion projects without consideration. However, the cyberneticians and the mechanists have attempted to save their thesis by using the notions of autocatalysis, fluctuation, and coupled systems. Let us examine their quote-unquote solution. They first remark, and on this point they are right in our view, that if the mathematical formula for the quantity of information and that for entropy are the same with opposite signs, a dissymmetry nevertheless appears between information and entropy. A machine cannot increase the precision of the information that it transmits, but it can, quote-unquote, extend it. The printing presses of a newspaper cannot correct the typos in the headlines, but they print the article in thousands of copies. If we consider no longer the quantity but the extension of information, there is no incompatibility between the normal increase of entropy and the extension of information. The printing presses of a newspaper, when they operate and print thousands of copies, consume electrical energy, which they usually degrade into heat. The result of their operation is therefore both the extension of information and the increase of entropy. The chemical phenomenon of autocatalysis, so important in organic structures, must be an extension of information of this kind. The molecule of the autocatalyst imprints, in a way, its form on billions of neighboring molecules. On the other hand, it is in no way contrary to the principles of thermodynamics that locally, in a non-isolated system and through energetic exchange with the rest of the world, or a bigger system, entropy can be decreased rather than increased, provided that the total increase be higher than the decrease. While living beings are clearly non-isolated systems. To say that they can contravene Carnot's principle by implying that they thus have a completely special and extraordinary property is, as the cyberneticians and mechanists emphasize, to play on words. They always represent coupled systems. What would be extraordinary if they were isolated is not at all extraordinary if we consider the, quote, organism food, unquote, or, quote, organism sunlight, unquote, system as a whole. The freezing of water in a freezer is not surprising, as would be the highly improbable freezing of water on a hot stove, because the freezer uses electricity like the printing presses of a newspaper. Like all heat engines, the freezer creates a local, quote-unquote, order at the price of a larger and more general, quote-unquote, disorder. The photosynthesis of plants is a reaction that miraculously appears to go uphill instead of downhill. But it should not be forgotten that the plant molecules capture quanta of light that directly provide them with the energy necessary for this uphill climb. The quote-unquote plant light system goes downhill, although the plant considered in isolation goes uphill and appears to increase the amount of free energy by decreasing entropy. Consider a staircase leading to a floor made of fine gravel. If there's no wind or rain, the gravel cannot go back up the stairs. However, a heavy rain can cause many small stones to jump down to the lower steps, and a very small number can jump up by chance to an extraordinarily improbable height. These notions of coupled systems, fluctuations, and autocatalysis would thus provide a means of understanding how living organisms, while obeying the ordinary laws of physics, can not only extend information but also increase its quantity by increasing the complexity of their structures. One can indeed consider the genes as autocatalytic molecules that imprint their quote-unquote order throughout the visible organism. For example, the molecules of chlorophyll can have their quote-unquote mole, or their quote-unquote type, in the germ of the plant. And on the other hand, which is the most important thing, the structures of molecule types themselves can result from an accumulation of mutations provoked by ultraviolet rays, gamma rays, and cosmic rays, which gradually, quote, build them up, unquote. In sum, the phenomenon of photosynthesis provides the principal elements of this attempt to reconcile the irreconcilable. The construction of living organisms is a sort of giant photosynthesis. Organic structures are built up by the accumulation of mutations caused by the more energetic photons, and on the other hand, the flow of energy with which the organisms are quote-unquote coupled easily explains the local uphill movements in the operation of these structures. It's as if the water would first form the mill and would then make the wheel turn. Even psychological intention can be conceived as a kind of Brownian motion concerning not movements of molecules but cerebral states, some fortunate fluctuations of which are captured and maintained. The man who telephones another is not then, in reality, a creator of information. He is like a mill on a quote-unquote current of order, or quote negative entropy, unquote, which he degrades, like any other real system, but by channeling the current in such a way that local uphill movements are temporarily possible. The energy necessary to telephone is taken from food ingested in the previous days and the structure of the message itself. That is, the complex channelings that transform the food energy into quote-unquote discourse energy, unquote, result from organic and social structures constructed progressively since the living species became civilized man by mutations, selections, and retentions. Maybe I'll stop here because we have sort of this long passage about this attempted solution. So this is sort of what I was talking about previously about how the local increase of information or decrease of entropy or increase of order, however you want to present it, this local sort of uphill movement or contrary to the gradient movement is always sort of brought about by a larger or a more global downhill or down gradient movement. So it's only because we as living beings take in structured materials like, in our food. We have, for example, carbohydrates in our food that we can break down and use the energy stored in the chemical bonds of our food. And then, when we, for example, move our muscles, we break down those chemical bonds, and that, release of energy in that chemical breakdown is what allows our muscles to move. And so in the case of in the same thing, as the neurons in our brain, for example, are functioning, they use energy that's stored in chemical bonds to, move ions across a membrane, which allows for, voltage changes and so on. So all the operations that happen in our body that are sort of counter to the gradient of entropy. So have an increase of order or decrease of entropy, happening within our body. They always involve the release of energy from breaking down chemical bonds. And so in the sort of bigger picture, where you're not just sort of zoomed in on one cell or even on our body in isolation, but you're looking at the whole system of all the nutrients that we're taking in our food, and then where that food comes from is ultimately the energy flowing from the sun towards the earth. So that bigger system involves a larger downhill flow of energy, or an increase of entropy that sort of makes possible a local decrease of entropy. So this is sort of the way out of the problem that the cyberneticians are sort of pointing towards, is that sort of ultimately there is only the downhill, or the downhill flow of energy, or the down gradient flow of energy is the most fundamental sort of process. And then as a result of that, larger global loss of information or loss of order, increase of entropy, you can have a local sort of uphill process. So like the sort of the gravel in the staircase, I think, is a good example of this, because if you picture this staircase with gravel at the bottom, in sort of a closed laboratory setting, there's no wind or anything else, then of course the gravel is never going to travel up the stairs. It's just going to sit there doing nothing. But if the staircase is outside and there's a big storm, even a hurricane, for example, some of that gravel just as a result of that wind could be blown up the stairs, even multiple steps up the stairs. Every time there's a hurricane, you find these like surprising pictures of like, I don't know, a couch being blown like hundreds of meters away from the house where it was originally, etc. So you can have these sort of improbable events happen as a result of this input of energy into the system. But so he sort of points already, I think, to the problem here, is that what he's going to argue is a problem. So we have sort of two types of processes that maybe are not quite the same thing, or it's not obvious that they're the same thing. So we have, for example, so he gives the analogy of a mill, so like a water wheel. So like in the late 18th, early 19th century, before you had steam power sort of take over in England, a lot of the factories were run on water wheels. So you had a stream, flowing, the energy of the water, ultimately resulting from gravity, pulling the water downwards, and so the water is flowing towards the ocean, flows downhill with a certain velocity, so it has this kinetic energy, and then you put a wheel in the water that is pushed by the water, and then you can use that wheel to power machinery. And so this sort of wheel, water wheel powering the mill, is not itself produced by the downhill flow of water. There has to be this sort of outside process of a human being, cutting down a tree, making boards, putting them together in a certain way, etc. All these processes are not themselves brought about by the water flowing downhill. Whereas the type of explanation that the cyberneticians are trying to set in motion would be one, it's as if the water flowing downhill not only powered a wheel that had sort of been brought in from outside, but itself sort of assembled all the parts of the wheel into, it took all these different parts and put them together into a wheel, and then powered the wheel as it was flowing. So there's sort of two different things: is the coming together of all these elements, assembling something like a water wheel in the first place, and then also once the water wheel is assembled, powering it and producing, or giving the capacity to produce work, to use energy to do something that would otherwise be improbable. And these aren't necessarily the same things, or you have to at least give another argument for how this flow of water downhill can do something analogous to putting together a water wheel. And Ruyer is going to argue that this sort of second obligation hasn't been fulfilled by this cybernetic explanation of the origin of information or the origin of order as a result of this sort of local decrease of entropy that's powered by the global increase of entropy. So that's what he's going to get to in the next bit as we continue this passage.
You mentioned in the chat that Ruyer probably always has Bergson in mind, but this argument reminds me of Bergson's distinction between the tendency toward either matter, or the tendency toward matter, and then the kind of opposite tendency toward either memory or temporalization or life, on the other hand. And for Bergson, at least one way of looking at the difference is that these material processes are much more local, even if they're never entirely local, and if something like pure matter is, for him at least, kind of an abstraction, then the opposite tendency, the tendency toward memory or life, would be a kind of increasing non-locality, in the sense that, I guess in the same sense that a melody is kind of contracted in each of its notes, but is not sort of fully explicated in each of its notes. And yeah, I wonder if Ruyer has something similar in mind. I think that for both of them, the second tendency, and I don't know if Ruyer would use the language of tendencies, would be one in which there's a kind of centrifugal creation of order, as opposed to a centripetal one, as you see in the kind of more composites rather than holistic tendencies.
Yeah, there's a lot of sort of difficult questions that come up in relation to these sort of thermodynamic or information theoretic concepts. And so one, of course, is the concept of randomness or chance. Like what exactly do we mean by random, or something that has no order, for example. And so one sort of one kind of example that is sometimes used in this circumstance is, like, you think of a pack of cards, for example, a deck of cards. So you suppose you shuffle it thoroughly for 10 minutes. You're just shuffling, and then you deal a hand of 5 cards, and you get a royal flush right away. You would be pretty surprised, like, did I do something weird when I was shuffling? Like, this seems very improbable. But really, the royal flush, this particular combination of 5 cards is exactly as likely as any other combination of 5 cards. That no matter what combination of 5 cards you deal, that combination of 5 cards is exactly as improbable as the royal flush. But one strikes us as like unlikely, and the other strikes us as just completely, if you just get like a 2, a 7, whatever, like just random cards, you wouldn't be surprised at all. And so when we talk about like order, or suppose like you shuffle all the cards, and then you deal out the whole deck, and you find that it's like each suit is comes out in order. You get like the 2 of hearts, the 3 of hearts, etc. The 2 of clubs, 3 of clubs, and just all of them in order. You'd be extremely surprised by this. You'd think this combination, just shuffling the cards randomly and then getting each suit exactly in order would be just extremely improbable. But of course, any other order of cards that did come out, like just a sequence of cards with no particular, observable order in them would also be exactly as improbable as what happens. So it's hard to get a clear concept of what exactly we mean when we say that something is random or unordered. And of course, we can't really understand the concept of entropy without having some understanding of order or the lack of order. This also comes up, sort of a related concept in the case of like producing a random number. So like, on a computer, you can probably, I'm sure there's websites where you can just like, enter, a range and then get a random number within that range or whatever. And of course, if you use Python, for example, there's a rand function that you can use to produce a random number within a certain range. This is actually not really a random number. It's a kind of pseudo random number. It like all the processes that are occurring in your computer when you ask it to give you a random number are themselves deterministic. So often they use things like they take like the last decimal points on like the clock. So like down to like microseconds. They just take like those decimal points at the point where at the time when the process is running. So these numbers, of course, are like not really very meaningful. And because they, like the exact time that you are running that process is sort of semi-random, you're likely to get just numbers that have no sort of relation to each other and that are, hard to predict. But in principle, you can sort of use, you can actually sort of predict some of these, what is going to happen when you run this random function. Of course, it would usually just be so, like the calculation would be so complicated that it's not really worth doing. So in many cases, like things having to do with encryption or cybersecurity and so on involve some kind of like scrambling operation where you want to be able to take some message of some kind, like a password or whatever, and make it indistinguishable from a random process so that you can't take this scrambled version and then extract information or find what it was before the scrambling, unless you have like some sort of key that allows you to unscramble it. But often there's like more information sort of encoded in the scrambled version than you really recognize. So I forget exactly what it was, but there was something where even like the amount of time that it takes for the computer to sort of decode the message can provide information about like what the code is. So like if you sort of send a signal and you measure like the amount of time it takes to get a response, then you can actually use that information to extract something, some information about the code or the decoding process, and then you can use that information to work on or to facilitate decoding the message yourself. And so sorry, I forget where I was going with that, but it's sort of, I guess the general picture is that like if we want to think about information as sort of the counter or the contrary to randomness, and then so an increase in entropy is like an increase of randomness, then we have to have some sort of understanding of what we mean by random, and that turns out to be actually a lot harder to sort of get a clear concept of than maybe it seems at first. Or like even the sort of like the sort of cliche example of the monkeys that type out the works of Shakespeare at random. Any however many millions of characters there are in Shakespeare's complete works, any other combination of characters of exactly the same length is exactly as likely as that one to be produced at random. But of course, like some absurd string of characters that has no meaning, we would not be surprised if the monkeys did that. Whereas if the monkeys did in fact type out the whole works of Shakespeare just by playing with the typewriter, we would be very surprised. So yeah, it's quite difficult to, and it seems like maybe the concept of randomness itself already involves some understanding of a process, an ordered process that like you can't understand randomness without understanding something like a process that brings about structure. and so if you were to try to sort of conversely try to explain the processes in terms of like not being random, then you're kind of in a conceptual circle. So to answer Angus's question, so Angus asked in the chat here, aren't there many more combinations of completely random characters than the single string corresponding to Shakespeare's works? Yes. So if you suppose there's 1 million characters in Shakespeare's works. I'm sure it's more than that, but just for the sake of an example, suppose there's 1 million characters and you have 26 letters plus some punctuation. Say there's 50 signs that can appear at any given point in this string of 1 million characters. Then you have 50 to the power of 1 million, which of course is some absurdly large number of possible combinations of signs that could all fit together. So out of this whole set of possible strings of 1 million characters, the one that corresponds to Shakespeare's complete works is very unlikely to appear. But any other specific string, even if it's like just a sequence of the letter A 1 million times, that string is also just as unlikely. It's one out of that 50 to 1 million set, or some sequence of punctuation and letters that has no discernible pattern to it. So this single, like if you pick one specific outcome, that even if it has no sort of discernible pattern, it doesn't seem surprising in any way. This single outcome is exactly as likely or unlikely as the result that gives Shakespeare's works as a whole in discernible, readable, understandable form. So one is not more unlikely than the other. It's just that the set of all the different incomprehensible sequences of letters and punctuation and so on is much larger than the single string that has the Shakespeare's works as a whole. Right, and so we have this comment in the chat from Coffee. Welcome. Coffee says, in cryptography and quantum mechanics, we typically describe a process as having randomness or non-randomness as a property. When we describe the output as having that property, it's understood to be shorthand for saying that the process that gave rise to that output is the one that's random or not, and not the output. So this is like, so then that sort of just pushes the question back to the processes, and so we would need to understand what it is that makes one process random versus structured. And so what the sort of cyberneticians are trying to do is to explain the emergence of structure in terms of some sort of statistical processes, and these processes would themselves not be the result of structure, I guess, or maybe to back up a little bit or to explain a bit better. We want to understand where order comes from or where information comes from, and if we think of information as something unlikely in the whole sort of sea of unstructured potential alternatives that were around, then we want to know where does this unlikely starting point come from, or where does this unlikely ordered state of a system come from. And the sort of information theoretic or this cybernetic way of explaining this is to say that this is sort of locally unlikely, but it's part of a global system that actually is very likely. So like I think it might have been before you joined, but we were talking about how the emergence of life on Earth is sort of comes about through the input of energy from the sun, and you can see how these sort of the soup of chemicals takes on structure as a result of receiving this input of energy. But then, and so at a local scale, if you're just sort of zooming in on the Earth, you have this like emergence of structure, which would a priori be unlikely. But then if you zoom out to the whole solar system, you have this kind of sort of increase of entropy. You have the solar energy just being dissipated out into space, and so you have a system that is going from a highly structured state to a less structured state, which is what we would expect just statistically speaking. And yeah, so here we have a process that we understand as being sort of in alignment with just the statistics of something unlikely becoming more homogeneous and becoming more likely. Um, but then we like to understand this process, we have to have some sort of understanding of why is it that we think of the first state as being unlikely and then the second state or the outcome of this process as being likely. Um, and so there's a kind of conceptual circle in the sense that we're trying to give these explanations of the origin of this unlikely state in terms of a process that brings it about. But then to understand those processes, we need to have an understanding of why it is that the state at the beginning of the process was likely or unlikely, and then the state at the outcome of the process is likely or unlikely. So it's hard to, yeah, it's this kind of like circle of concepts that it's hard to sort of break into or to like figure out where we should start, with the processes or the states being likely or unlikely. Okay, Angus, would you like to read the next bit? I think we're at such is in some.
Yes, sorry. We're on 84.
I think we're on 85. Yeah, 85 at the square brackets there, such is in some.
Yeah, no problem. Such is, in some, the solution proposed by a multitude of contemporary scientists. Erwin Schrödinger, Harold F. Bloom, Pierre Auger, pronounce that, Norbert Wiener, and Joseph Needham. It is not essentially different to the old theory of Herbert Spencer, who also, quote unquote, explained the evolution, that is to say, the appearance of structures by coupling and integration of matter and a concomitant dissipation of motion. This quote unquote solution rests on multiple errors and confusions. The only valid thesis that it contains, namely that entropy and information, despite the symmetry of their mathematical formulae, are not perfectly symmetrical, is precisely what destroys all the rest of the argumentation. 1. The word order is equivocal. It designates either a homogeneous order, for example, all the water molecules in the current which make the mill wheel turn in the same direction, or a complex structural order in an organization structured at multiple levels. For example, the mill and the body of the miller have an organized structure. The normal evolution toward maximal entropy or disorder destroys order in both senses of the word. In the lower reservoir of the mill, the water molecules move randomly in all directions. And on the other hand, if nothing contradicts the laws of classical physics, the mill and the miller are destined to lose their structure through ruin and death. Information, on the contrary, is only order in the second sense of the word, despite certain apparent exceptions. Case 1. Balzac composed an entire chapter of his Physiology of Marriage using randomly chosen printing letters. Case 2. Suppose that another author, with a similarly humorous intention, composed an entire chapter using only the letter X. Case 3. The reader will have no more information in the one case than in the other, despite the homogeneity of the composition in the second case, and despite the perfect order of the pages entirely composed of X. In order for the printed characters to convey some information, they must be organized into words and phrases, themselves structured by the unity of a meaning. If we measure the quantity of information in the three cases, we find that the information is equal to 0 in the first case, the Balzac chapter, since the letters were chosen randomly, but that they have the same positive value in the second and third cases. This is contrary to reality, however, since the chapter composed of X's tells us nothing more than Balzac's chapter. More exactly, the quantity of quote-unquote Hartleys that we attribute to the chapter composed of X's will depend on our conventions. If we consider that each X was chosen as a significant letter of the chapter, the quantity of information is the same in both cases. If we assume that the author wanted to compose a chapter using only the same letter for the sake of humor, the amount of information should only be measured by the choice of that single letter. There's no need to reject the mathematical definition of the quantity of information for this reason, but it is important to recognize its superficial and relative nature. In the industrial printing of a European language, we employ around 80 characters, as 6 binary symbols, 1 and 0, have 64 possible arrangements and 7 have 128. Each character in a printed book basically corresponds to 7 units of information. In order to measure the quantity of information given by a print, it suffices then to multiply by 7 the number of characters used. This way of measuring does not distinguish between Newton's Principia, a collection of Carême's sermons, or a history book about Marseille, any more than a meter distinguishes between silk and cotton. The measure of information, like all measurement, must be made intelligently and relative to a certain mental context. If, for a re-edition of Balzac's book, a typographer is obliged to reproduce the typographical quote-unquote pudding of the first edition exactly, we can attribute a positive information value to his work relative to this intention. But the typographer would be better not to give himself this difficulty, which is absurd in the circumstances. We see therefore that in the second case, the idea of information is applied arbitrarily, and it is absolutely relative, although we can always measure it. In the third case, on the contrary, information is an absolute reality. The letters form phrases that have a meaning. It is not necessary to object here that for a Chinese person ignorant of French, there would not be any difference between case 1 and case 3, because we can translate the sense of 3 and not the sense of 1. It is no more necessary to object that it is again relative, at least to the presence of an intelligent reader, and that in the absence of a person, text 3 has no more meaning or quote-unquote absolute information than 2 or 1. That would return us to the assumption that the absolute information actually appears not in the person, but in the system, quote-unquote text-person. If we again object that text 3 has only been produced by chance among other possible combinations, and that in the absence of other consciousnesses, there would be no more meaning than with any other fortuitous combinations, we are perfectly right. But with this, we then admit, contrary to the thesis itself, that chance on its own cannot create authentic information. So, as I understand the argument in this first section of the criticism of the cybernetic understanding of information, part of it is that this measurement of information is purely quantitative and depends on how we decide to classify the choices that went into the composition of some message. So, for instance, a message that's composed of all X's, if each X was somehow independently chosen, then there would be a much greater quantity of information than if the letter was just chosen once, even though the message itself doesn't really change. It's still, a chapter full of X's. The measure of the quantity of information would differ depending on how we understood the intention of the author.
Yeah, so here, this example with the X is a little bit hard to understand, but I guess the idea is that you can only measure the information content of a message, like even this sort of quantitative communication theoretic account of the information content of a message can only be measured in relation to a sort of underlying set of possible messages. So if you know, for example, that the message is being transmitted from a keyboard that has precisely one letter, it only has the letter X, for example, then the only information that you're really getting from that message is how many times the person pressed that single letter. Whereas if you're being transmitted a message that comes from a regular keyboard, then you have the 26 letters plus numbers and other signs. And so if you get exactly the same message that consists only of the letter X, then you're going to be getting a different sort of content of information because you're selecting one out of, I don't know, say 50 signs as opposed to one out of one sign. And so before you can even measure the content of information or the quantity of information that a message contains, you have to know what other possible messages could have been transmitted. It's not obvious, at least, that this sort of knowing what the initial set of possible messages was can itself be understood in terms of transmitting information and what is probable or improbable. So like it seems that before we can even decide what is probable or improbable, we have to know what is possible at all in the first place. We have to have some sort of set of possible events before we can sort of assign a probability to some of those events and say, these ones are, have probability X and these other ones have probability Y, etc. So we need to have that like underlying base of possibilities before we can even assign a certain value to the probability of those events, and then use that probability to determine how much information we can receive by transmitting using some of these probabilities. So this sort of very quickly gets us into like very deep and obscure questions about what does it mean for something to be possible or impossible, probable or improbable, like what is chance, what is randomness, etc. It doesn't seem very likely that we'll be able to sort of get around these problems just by measuring how much information can be transmitted over a certain telephone line and sort of similar types of procedures. It seems that we have to already presuppose some kind of answer to those questions before we can even start measuring like the information transmission capacity of a telephone line. So it's not obvious that we can sort of get away from the more fundamental questions about randomness and possibility and so on just by this sort of technical trick of measuring information. Yeah, and I guess I mentioned Bergson again in the chat here, and so like this is something that Bergson talks about in terms of like when he's in the immediate what's the translation? Immediate givens of consciousness, I guess. I can't remember the exact translation of the title, but in his first book, he talks about he's looking at like sort of free will versus determinism, and he sort of argues that both pictures. Oh, time and free will. Okay, that's like a completely different title. So he considers both pictures in sort of the indeterminist and determinist pictures of human action as sort of presupposing that there's a pre-given set of like possible actions that like, I don't know, you're sort of at a crossroads and you either go left or go right, but these two options are already sort of virtually present. And then the question is just like, is your decision to, I don't know, go on the left path versus the right one, was that decision sort of like made freely, or like could you have gone to the right instead, or was there some sort of like process or force or whatever that made it such that you were always going to go left no matter what? And he thinks this is kind of like a misunderstanding of decision making or action, because it's sort of inscribing the possible actions in the world before the action is actually done, as opposed to having the action be a kind of invention or creation of something that didn't already exist. So this, like, if we want to sort of apply information theoretic concepts to like human actions, and especially things like invention, creativity, etc., then we would need to already have that sort of virtual invention be there. Like you can think of, say, like, I don't know, whatever, writing a novel, for example, that like the novel was sort of virtually there in this whole sequence of potential strings of characters, right? That like what you're doing as a novelist is essentially just like, out of all the billions of possible sequences of characters of X length, you are selecting one of those characters, one of those strings. And this is, I mean, in one sense, this is correct. Like, of course, there is, like, we have a finite sort of alphabet of characters that are printed, that we can print on a page, and the novel is precisely one of those strings. But it also kind of like misrepresents what exactly a novelist is doing, because, of course, most novelists, maybe there are some sort of like experimental novelists who use some sort of process like this. I know there's like automatic writing and some of those types of methods. but for most people who are writing a novel, they don't do so by sort of you know selecting among many sort of possible strings, most of which are completely meaningless. They do so. They think about plot and character and setting and these more sort of conceptual categories that involve some sort of understanding of this fictional world, or and maybe what that tells us about our actual world and so on. Yeah, so it's something very different than just like selecting one string of characters out of the base of all the billions of other possible strings of characters. So yeah, I think he wants to. So what both Bergson and Ruyer want us to do is to sort of shift the focus away from this like selection of one option out of many that were virtually present towards a conception of invention as a creation of something that didn't already exist, even in this sort of virtual sense, or this like sort of ghost accompanying the actual world. And there's a much later text from Bergson where he sort of applies a similar conception of like possibility, or arguments about possibility in relation to the question of why is there anything at all and not rather nothing. And he sort of argues that this is a question that doesn't really make sense, in the sense that it sort of like presupposes a kind of like possibility of there not being anything as sort of accompanying or like alongside the world, this sort of virtual non-existence that would just be sort of like a possibility that could have been the actual world, but just as a matter of chance didn't, or for whatever reason, that we were trying to find the reason why that world was not the one that became actual, as opposed to the one that did, which has entities in it. And for him, this is a sort of like flipping the concepts of like contingency and possibility and so on like on their head, and kind of making the possible worlds or possible alternate realities into like what exists first, and then out of that set of like possible worlds, including the one that has nothing in it, you would need to find a way of explaining why this particular one is the one that was realized. And of course, you could use like a Leibnizian, optimization of the amount of existence, and argue that this world is the best of all possible worlds and so on. But yeah, for Bergson, this is like sort of starting from the wrong point in the whole sort of understanding of contingent events and decisions being made and so on, and then like starting from this sort of backwards point of view, then sort of trying to get back to the real world, and that's like just fundamentally confusing what it means to say something is possible. Yeah, Bergson is one of these guys that I think I might have said this before, but like when you read him, like everything seems very like sort of easy. Like he has this very elegant sort of style of writing, and he won the Nobel Prize for Literature, and so like many people who were not philosophers were reading his work and just like maybe sort of appreciating the style and so on. But yeah, so it may be like if you just sort of read like quickly, it doesn't really seem that like sort of deep, or like maybe it's just kind of superficial. But then when you sort of stop and think about what he's saying, it's actually he's really getting to, I think, important problems. Even if sometimes his solutions maybe you don't agree with, or maybe are not like that satisfying. Like the problems that he's like pointing to, I think are really important ones. And like every time that I go back to Bergson, or I read someone who is like working with his concept or criticizing him or whatever, I always sort of have a new appreciation for like how just how good Bergson is as a philosopher, even if it like doesn't necessarily seem to be the case when you're just sort of reading quickly and not thinking very carefully about what he's presenting. Okay, so we are approaching the 2-hour mark, so maybe we can stop here and then pick up from page 87 next time.
Sounds good to me.
Okay, cool. Thanks everyone for coming out, for your contributions, and hope to see you next time.